The HAARP site was constructed in 3 distinct phases, each building on the last. First, we had the developmental prototype, or DP, with its 18 antenna elements, generating 360 kilowatts of power, just enough for basic ionospheric testing. Then came the filled developmental prototype, or FDP, boasting 48 antennas and a power boost to 960 kilowatts. This phase allowed for numerous successful scientific experiments and exploration campaigns. Finally, we reached the final IRI, or FERI, featuring 180 antennas and a staggering 3.6 megawatts of transmitter power. This setup enables a theoretical gain of 31 dB, focusing energy upward with precision. By summer 2007, it was fully operational, achieving an effective radiated power of 5.1 gigawatts. While it typically runs at lower power levels, its capabilities are impressive. Other related facilities like HAARP in Alaska and U.S.A in Norway highlight the global interest in ionospheric research. The High-Frequency Active Auroral Research Program, or HAARP, is a fascinating initiative based at the University of Alaska Fairbanks. At its core is the Ionospheric Research Instrument, a powerful transmitter that temporarily excites the ionosphere, the highest part of our atmosphere. This facility, which began construction in 1993 and became fully operational in 2007, was initially funded by the U.S. military to explore radio communication technologies. With an investment of around $250 million, HAARP employs various instruments like radars and magnetometers to study the physical processes in the ionosphere. Despite its scientific purpose, HAARP has become a magnet for conspiracy theories, with claims of weather manipulation. However, scientists assert that these theories are unfounded and far beyond the facility's capabilities. The HAARP antenna array is a fascinating project that directs a powerful 3.6 MHz signal into the ionosphere, exploring frequencies between 2.8 and 10 MHz. This research helps us understand natural processes influenced by solar activity and how the ionosphere affects radio signals. The insights gained here are crucial for enhancing communication and navigation systems, with applications ranging from improved GPS accuracy to advanced submarine communication. Originally funded by the Office of Naval Research, HAARP involves collaboration with numerous prestigious universities, ensuring a wealth of knowledge and innovation. The project prides itself on transparency, allowing scientists from around the world to access the facility and share findings in major research journals. With annual open houses, anyone can explore this cutting-edge research hub, making HAARP a unique blend of science and community engagement. HAARP's primary mission is to dive deep into the mysteries of the ionosphere, that fascinating layer of our atmosphere where the air is thin enough for the sun's X-rays and UV rays to penetrate, yet dense enough to hold a wealth of information. Picture this. Starting at about 70 kilometers above us, free electrons begin to surge, peaking around 300 kilometers, and then tapering off as we approach the edge of space. This dynamic region is constantly shifting, influenced by everything from solar activity to seasonal changes. Measuring the ionosphere has always been a challenge. Balloons can't reach it, and satellites can't orbit there. That's where HAARP comes in, building on the groundbreaking work of U.S.A in Norway. By sending powerful radio waves into the ionosphere, HAARP can perturb this complex layer and observe its reactions in real time. It's like tuning into the universe's own radio station, revealing secrets that have eluded scientists for decades. HAARP is a fascinating facility with some remarkable capabilities. It generates very low-frequency radio waves by modulating the heating of the auroral electrojet, which is a game-changer since traditional methods require massive antennas. It can even create artificial airglow, bright enough to see under the right conditions. Then there are the extremely low-frequency waves, which are nearly impossible to produce otherwise due to their long wavelengths. HAARP also generates Whistler mode VLF signals that travel into the magnetosphere, interacting with particles in the Van Allen radiation belts. Its research spans a wide array of topics, from plasma line observations to the effects of meteor showers on the ionosphere. They've even studied polar mesospheric summer echoes using multiple radar systems, helping us understand these elusive phenomena. The facility has been instrumental for the military, enhancing submarine communications over vast distances. It's incredible how HAARP contributes to our understanding of the ionosphere and its impact on technologies like GPS, all while pushing the boundaries of atmospheric science. During active ionospheric research, we transmit signals from our advanced transmitter system to an antenna array, sending them skyward. As these signals reach altitudes between 70 and 350 kilometers, they interact with the ionosphere, getting partially absorbed in a small volume. Interestingly, the intensity of our high-frequency signals is less than 3 UWW-cm2, minuscule compared to the sun's electromagnetic radiation. Yet, these subtle effects can be detected by the sensitive instruments at the HAARP facility, revealing crucial insights into plasma dynamics and solar-terrestrial interactions. Our antenna elements are designed as cross dipoles, capable of transmitting in both ordinary and extraordinary modes. Operating between 2.7 and 10 MHz, we carefully manage our effective radiated power, especially at lower frequencies where losses are higher. We can transmit continuous waves or short pulses, with the latter often used for radar applications. By modifying the ionosphere and then measuring the decay of these modifications, we unlock the mysteries of our atmospheric interactions, pushing the boundaries of what we know about our planet's upper atmosphere. At the HAARP facility in Alaska, a fascinating array of geophysical instruments is at work. One standout is the FluxGate magnetometer from the University of Alaska Fairbanks, which tracks variations in the Earth's magnetic field. These rapid changes can signal geomagnetic storms, giving us crucial insights into space weather. Then there's the Digisonde, which provides detailed ionospheric profiles, helping scientists select the best frequencies for ionospheric research. The University of Tokyo contributes an induction magnetometer that measures geomagnetic fluctuations in the ultra-low frequency range, from 0 to 5 Hz. Powering all this are 5 massive 2,500 kilowatt generators, driven by robust diesel locomotive engines. Located just north of Gakona, this site, once home to an over-the-horizon radar installation, now hosts up to 180 antennas, making it a hub for cutting-edge geophysical research. Various individuals have raised alarms about HAARP, suggesting it could be a military weapon. Rosalie Bertell warned as early as 1996, while Michel Chossudovsky pointed to its potential to trigger catastrophic events like floods and earthquakes. Over the years, HAARP has been implicated in disasters across the globe, from hurricanes in the Philippines to power outages in Turkey. Nick Begich Jr. claims it can manipulate the atmosphere, even turning the sky into a burning lens. Russian military sources warn of its ability to flip Earth's magnetic poles. The Alaska legislature and the European Parliament have held hearings, with concerns about environmental impacts. Jesse Ventura questioned its use for mind control, while physicist Bernard Eastlund asserted it could modify weather patterns. In 1998, a report from the European Parliament, based solely on testimonies from Begich and Bertell, labeled HAARP a global concern, calling for an independent investigation into its implications. The mystery surrounding HAARP continues to fuel speculation and fear.
Stanford professor Omrin Inan emphasizes that despite HAARP's powerful emissions, they pale in comparison to natural phenomena like lightning, which occurs 50 to 100 times every second. The University of Alaska Fairbanks has recognized this issue and now hosts annual open houses to demystify its work. Yet even recent events, like the 2022 UN Climate Change Conference and the earthquakes in Turkey and Syria, have reignited conspiracy theories, linking HAARP to geoengineering and seismic activity. The reality is, while HAARP may spark curiosity, It's crucial to separate fact from fiction in the realm of science.